How does information move through empty space without anything visibly carrying it? Not through wires, not through tubes or channels, but through the air itself, quietly, constantly, all around us. Right now, as you listen to this, countless signals are passing through the room you're in. They're crossing your walls, your body, the furniture around you. They're overlapping, interfering, fading, strengthening, and disappearing again. And yet, out of all of that motion, your device manages to pull out a single, stable stream of information. A voice, a sound, a connection, as if it were being handed directly to you. That quiet miracle is what we call Wi-Fi. At its surface, Wi-Fi feels almost too ordinary to be strange. We expect it to work. We only notice it when it doesn't. But once you slow down and look carefully at what's actually happening, it becomes one of the clearest examples of how deeply physical the modern world really is. Because Wi-Fi is not abstract. It is not digital in the way we often imagine. It is a physical process, unfolding moment by moment, governed by the same laws that control light, radio waves, and the behavior of electrons themselves. And that makes it something we can understand. Before we go any further, let me take a quiet moment here. If you find yourself enjoying this way of exploring physics, slowly, carefully, without rushing to conclusions, a gentle like or a soft tap on subscribe helps keep this calm corner of the universe going. It makes space for conversations like this to exist. All right, let's stay with the idea. To understand Wi-Fi, the first thing we need to let go of is the idea that information is something separate from the physical world. It isn't. Information always rides on something real. It needs a physical carrier, a change, a motion, a pattern, something that can exist in space and time. For Wi-Fi, that carrier is an electromagnetic wave. Electromagnetic waves are not objects moving through space. They are patterns, coordinated changes in electric and magnetic fields that sustain one another as they travel. When an electric field changes, it creates a magnetic field. When a magnetic field changes, it creates an electric field. Linked together in this way, the disturbance becomes self-propagating. It moves outward, not because something is being thrown, but because the fields themselves are rearranging continuously. This is the same phenomenon that gives us visible light. The difference is scale. Visible light oscillates extremely fast, with wavelengths small enough to interact with the molecules in our eyes. Wi-Fi uses much longer wavelengths, typically a few centimeters, oscillating billions of times per second, but still slow enough that they pass straight through walls, clothing, and most everyday objects with ease. When your router sends a Wi-Fi signal, it does not send bits or packets in the abstract sense. It sends an oscillating electromagnetic field into the surrounding space. That field spreads outward in all directions, weakening as it goes, shaped by reflections, absorption, and interference from the environment around it. This field is entirely physical. It fills the room. It fills the building. It spills out into the street. The information comes from how that field is shaped. Imagine holding a rope fixed at one end and gently shaking it. You can shake it slowly or quickly. You can shake it with small motions or large ones. You can change the rhythm, pause, resume, alter the pattern. Someone watching the rope can tell exactly what you're doing by observing those changes. You are not sending instructions down the rope. You are creating a pattern of motion, and that pattern carries meaning. Wi-Fi works the same way, except the rope is the electromagnetic field itself. At the router, tiny electronic circuits control the oscillation of an antenna. That antenna pushes and pulls on the surrounding electric field, creating waves whose properties are carefully adjusted. The frequency is set by design. The strength is controlled by power limits, and the information is encoded by small, precise variations, shifts in phase, amplitude, or timing, layered on top of the carrier wave. Nothing about this is symbolic at first. There are no ones and zeros in the air. There are only continuous physical changes. The digital world exists because both the transmitter and the receiver agree on how to interpret those changes. Your device, sitting quietly across the room, is not waiting for a message in the way a mailbox waits for a letter. It is immersed in a constantly changing electromagnetic environment. Its antenna responds to that environment automatically. As the electric field around it oscillates, electrons inside the antenna are pushed back and forth. Their motion generates tiny electrical signals in the circuitry, signals that mirror the structure of the incoming wave. From there, the process reverses. Physical motion becomes electrical variation. Electrical variation becomes a measured pattern, and that pattern, once stabilized and interpreted, becomes information again. Not because the universe knows what a message is, but because we've built systems that consistently map physical states to meaning. This is where things begin to feel delicate. Wi-Fi does not operate in a clean, empty space. Every signal shares the air with countless others. Phones, laptops, routers, Bluetooth devices, microwaves, even distant transmitters outside your home. All of them contribute to a background of overlapping electromagnetic activity. The waves pass through one another without colliding, but their effects add together at the receiver. The result is not silence plus signal. It is always a mixture. The reason Wi-Fi works anyway is not because the signal is perfectly isolated, but because it is structured. Modern Wi-Fi systems divide the available frequency range into narrow channels and then divide time itself into coordinated intervals. They spread information across multiple frequencies at once, using patterns that can be recognized even when parts are distorted or lost. This is not brute force. It is geometry and timing. It is the careful use of redundancy and correlation, allowing the receiver to reconstruct the intended pattern from incomplete physical evidence. If that sounds almost fragile, that's because it is. Every wall slightly reshapes the wave. Every reflection creates a delayed copy. Every moving object introduces small shifts. And yet, from this constantly shifting field, stable communication emerges. Not because the physics is simple, but because it is reliable. Electromagnetic waves behave predictably. Their interactions can be anticipated, and once you understand those behaviors, you can build systems that lean into them rather than fight them. At this point, something important should be clear. Wi-Fi is not fast because information is somehow skipping through space. It is fast because electromagnetic interactions propagate at the speed set by the structure of space itself. The same constant that governs light governs Wi-Fi. The same field equations apply. There is no separate wireless physics hiding underneath. There is only electromagnetism, patiently doing what it always does. And this is where the deeper question begins to form. If Wi-Fi is nothing more than carefully shaped electromagnetic motion, and if that motion fills the space around us continuously, then the real mystery is not how information moves through the air. It's how space itself can support such motion at all. Why electric and magnetic fields exist. Why they propagate. Why they obey the relationships they do. Those questions sit quietly beneath every connection we make, and they're where we need to look next. The reason those questions matter is that Wi-Fi is not choosing its behavior freely. It is constrained by scale. Every electromagnetic wave has a frequency, and frequency is not just a number. It is a physical rhythm. It tells you how quickly the electric and magnetic fields are oscillating as they move through space. Faster oscillations mean shorter wavelengths. Slower oscillations mean longer ones. And that single relationship quietly determines almost everything about how a signal behaves in the real world. A wavelength is simply the distance over which the wave repeats its pattern. It is the physical size of one oscillation laid out in space. For visible light, that distance is smaller than a micrometer. For Wi-Fi, it is closer to the size of your hand. And that difference changes how the wave interacts with matter in a very direct way. When a wave encounters an object, it does not ask what the object is made of first. It asks how large the object is compared to itself. If the object is much smaller than the wavelength, the wave barely notices it. If the object is comparable in size, the wave is reshaped. If the object is much larger, the wave is reflected, absorbed, or redirected. This is why Wi-Fi passes through walls that visible light cannot. The individual structures inside most walls, wood fibers, drywall crystals, air gaps, are small compared to a Wi-Fi wavelength. The wave averages over them. It bends slightly, weakens slightly, but continues on. Visible light, with its much shorter wavelength, interacts with those same structures far more strongly. It scatters, reflects, and is quickly blocked. The same logic explains why Wi-Fi antennas have the size and shape they do. An antenna is not an arbitrary piece of metal. It is a structure designed to resonate with a particular wavelength. When the length of a conductor is matched to the scale of the wave, the electrons inside it respond efficiently. They move back and forth in step with the oscillating field, exchanging energy smoothly between the circuit and the surrounding space. If the antenna is too small, it barely couples to the wave at all. If it is too large, different parts of it experience different phases of the wave at the same time, and the motion cancels itself out. Efficient transmission and reception only happen when geometry and wavelength are in quiet agreement. This is why Wi-Fi lives where it does in the electromagnetic spectrum. Frequencies that are too low require antennas that are physically large and slow to respond. Frequencies that are too high behave more like light, reflecting sharply, requiring precise alignment, and struggling to spread around obstacles. The bands used for Wi-Fi sit in a middle region where antennas can be compact, walls are semi-transparent, and signals can fill rooms without being tightly aimed. But frequency does more than set scale. It also sets capacity. Every oscillation of the electromagnetic field is an opportunity to carry variation. The faster the field oscillates, the more finely you can shape it in time. This is why higher frequencies can support higher data rates. Not because they move faster through space, they don't, but because they give you more structure per second to work with. This creates a trade-off that quietly governs all wireless communication. Lower frequencies travel farther and penetrate more easily, but they offer fewer degrees of freedom for encoding information. Higher frequencies can carry more detail, but they are more easily disrupted and absorbed. Wi-Fi exists in a region where this balance is workable indoors, where the environment is cluttered, reflective, and constantly changing. Once you see this, the behavior of Wi-Fi begins to feel less mysterious and more inevitable. Its range, its speed, its fragility near walls or corners, all of it follows from wavelength interacting with space. Nothing is arbitrary. Nothing is hidden. The physics is doing exactly what it must. And yet, frequency alone is not enough to make communication possible. Even a perfectly chosen wavelength would be useless if there were no reliable way for a device to exchange energy with the electromagnetic field in the first place. The wave can pass through space all at once, but unless something is able to feel its motion and respond to it coherently, the information it carries never becomes accessible. That connection between moving fields and moving charges is where things become more tangible. Because the moment a wave reaches an antenna, space is no longer empty. The moment an electromagnetic wave reaches an antenna, the abstract idea of a field becomes something physical again. An antenna is not a receiver in the sense of a container waiting to be filled. It is a structure placed into space so that it cannot avoid responding to what the fields around it are doing. When the electric field of a passing wave oscillates, it pushes on the charged particles inside the metal. Electrons shift, ever so slightly, back and forth along the conductor. That motion is not optional. It is a direct consequence of the field interacting with matter. This is where the boundary between space and device quietly dissolves. The antenna doesn't extract energy from the wave in discrete chunks. It couples to the field continuously. As the field changes, the charges respond. As the charges move, they generate their own fields, feeding energy into the connected circuitry. The process is smooth, analog, and governed entirely by electromagnetism. Nothing digital happens here yet. There is only motion and response. The efficiency of that response depends on resonance. Every physical system has natural rhythms at which it prefers to move. A guitar string vibrates most easily at certain frequencies. A swing responds best when pushed in time with its motion. An antenna behaves the same way. When the length and shape of the conductor match the wavelength of the incoming signal, the oscillating field drives the electrons efficiently. Energy flows easily between space and circuit. When they are mismatched, the response weakens, and much of the wave passes by with little effect. This is why antennas are tuned. Tuning is not about selecting a channel or filtering information. It is about geometry. By choosing the dimensions of an antenna, engineers choose which wavelengths it can interact with most strongly. Everything else becomes background, still present, still physical, but far less effective at inducing motion in the charges. Inside the antenna, the electrons do not move far. Their displacement is tiny, often smaller than the size of an atom. But their motion is collective. Trillions of charges shift together, and that coordinated movement creates a measurable electrical signal. The shape of that signal mirrors the shape of the electromagnetic wave that caused it. Variations in amplitude, timing, and phase are preserved because the physics demands they be preserved. From here, the signal leaves the antenna and enters the receiver circuitry, where it is amplified, stabilized, and prepared for interpretation. But even at this stage, nothing has been decoded. The system has not yet decided what the signal means. It has only transformed a pattern in space into a pattern of voltage over time. That transformation works in reverse as well. When a transmitter sends a Wi-Fi signal, it begins with carefully controlled electrical currents in a circuit. Those currents are driven back and forth at specific frequencies, shaped with deliberate variations. When they reach the antenna, the moving charges generate changing electric and magnetic fields. Those fields detach from the metal and propagate outward, becoming waves that fill the surrounding space. The antenna is not launching objects into the air. It is setting boundary conditions on the electromagnetic field, forcing it into motion. The wave does not originate at a point. It emerges everywhere the field is being disturbed in a coordinated way. This symmetry is important. Transmission and reception are not fundamentally different processes. They are mirror images of the same interaction. In both cases, energy flows between matter and field according to the same rules. What changes is the direction of flow and the intent behind the shaping. Once you see this, the idea of sending and receiving becomes less mysterious. Devices do not reach out to grab signals, and signals do not seek out devices. Both are immersed in the same electromagnetic environment, continuously exchanging energy whenever their structures allow it. But this still leaves an unresolved problem. If antennas respond to any matching electromagnetic motion in their environment, how can they possibly distinguish the signal they care about from all the others passing through the same space? How does a receiver avoid being overwhelmed by everything at once? The answer is not isolation. It is structure layered on structure, imposed carefully in time. And that brings us to how variation itself becomes information. To understand how variation becomes information, it helps to notice something subtle about the signal arriving at the antenna. The wave itself is smooth, continuous. There are no gaps between moments. No built-in markers that say where one piece of information ends and another begins. The electromagnetic field does not know what a message is. It only knows how to change. And yet, those changes are not random. At the most basic level, a Wi-Fi signal is a repeating oscillation at a well-defined frequency. That oscillation is the carrier. It provides a stable, predictable rhythm, a physical reference that both transmitter and receiver can agree on. Without that shared rhythm, there would be no way to distinguish intentional variation from noise. Information is added by gently disturbing that rhythm. One way to do this is by changing the strength of the wave. If the oscillation grows slightly stronger for a short time and then weaker again, that variation can be detected. Another way is by shifting the timing of the oscillation, nudging the wave forward or backward in phase relative to a reference. Yet another is by switching between closely spaced frequencies. Each of these methods alters the wave in a controlled way while preserving its overall structure. What matters is not the absolute value of any single oscillation, but the pattern formed across many of them. This is where the idea of bits begins to emerge, not as physical objects, but as decisions made by the receiver. The receiver does not measure a wave and find a 1 or a 0 embedded in it. Instead, it measures a continuous signal and asks a series of questions. Is the phase closer to this value or that one? Is the amplitude above or below a threshold? Is the timing early or late compared to expectation? Each answer collapses a range of physical possibilities into a discrete interpretation. This process depends critically on agreement. The transmitter and receiver must share the same conventions. They must agree on which variations matter, how finely they will be distinguished, and over what time window a decision will be made. These agreements are not laws of physics. They are design choices layered on top of physics. But once chosen, they become constraints that shape how information flows. What makes this remarkable is that the underlying signal never stops being analog. No matter how digital the system appears at higher levels, the electromagnetic wave remains continuous. The voltages in the antenna fluctuate smoothly. The currents in the circuit vary without jumps. Digital behavior emerges only after careful measurement, comparison, and interpretation. This is why noise is unavoidable. Any real physical system is subject to random fluctuations. Thermal motion jostles electrons. Distant transmitters leak energy into the same frequencies. Reflections arrive slightly delayed and slightly distorted. None of this can be eliminated entirely. The receiver never sees a pristine signal. It sees a superposition of influences and must decide probabilistically what was intended. Wi-Fi does not fight this uncertainty by demanding perfection. It embraces it. Instead of encoding information into a single fragile variation, modern Wi-Fi spreads information across many dimensions at once. Time is divided into short intervals. Frequency is divided into narrow bands. Phase and amplitude are adjusted in coordinated patterns. Even if some pieces are corrupted or lost, the overall structure can still be recognized. This approach relies on correlation. A random fluctuation may disturb one part of the signal, but it is unlikely to mimic the full pattern expected by the receiver. By looking for consistency across many measurements, the receiver can distinguish meaningful structure from background randomness. Errors are detected, and when necessary, information is requested again. This is not because the physics is forgiving, it is because it is predictable. Electromagnetic waves obey linear rules over the ranges Wi-Fi uses. When two waves overlap, their fields add. When a wave reflects, it follows geometric constraints. When it weakens with distance, it does so smoothly. These behaviors can be modeled, anticipated, and compensated for. The system does not need to know exactly what the environment will do. It only needs to know how deviations will tend to behave. This predictability allows time to be used as a resource. Rather than sending information continuously without pause, Wi-Fi systems divide transmission into short bursts. Each burst carries a packet, a structured block of variation with a known beginning and end. The receiver aligns itself to these boundaries using synchronization signals embedded in the wave itself. Once aligned, it knows when to expect meaning and when to ignore fluctuations. Time, in this context, is not a backdrop. It is an active participant. Small errors in timing matter. If the receiver's internal clock drifts too far from the transmitter's, the structure of the signal blurs. Decisions become ambiguous. This is why Wi-Fi devices constantly resynchronize, adjusting their internal rhythms to match the incoming field. The shared sense of time is maintained dynamically through continuous feedback. Distance enters the picture here in a subtle way. Inside a room, the time it takes for a Wi-Fi signal to travel from router to device is extremely short, measured in nanoseconds. Compared to the timescales of encoding and decoding, this delay is negligible. What matters more is not how long the signal takes to arrive, but how many delayed copies arrive along with it. Every reflection off a wall or object creates a slightly delayed version of the original wave. At the receiver, these copies overlap. Sometimes they reinforce one another. Sometimes they partially cancel. The resulting signal fluctuates depending on position, orientation, and motion. This is why moving your device by a few centimeters can change reception quality dramatically. Rather than treating this as a flaw, Wi-Fi systems treat it as information. By observing how the signal changes across multiple antennas or over short intervals of time, the receiver can infer the structure of the environment. It can identify stable paths and unstable ones. It can weight contributions differently, favoring those that arrive consistently. In effect, the system learns how space itself is shaping the wave and adapts accordingly. This adaptation happens continuously, invisibly, and without awareness. From the listener's perspective, the connection either works or it doesn't. But underneath that simplicity is a constant negotiation between fields, matter, and time. A negotiation that never settles into a static state, because the environment never does. All of this brings us back to a quiet but profound point. Wi-Fi works not because space is empty, but because it is structured. The electromagnetic field is not a medium in the old mechanical sense, but it has properties. It supports waves. It enforces limits on speed. It links changes in one place to changes elsewhere in a precise way. Those properties are stable enough that we can build communication systems on top of them, confident that they will behave tomorrow as they did today. And yet, the field itself does not carry intention. Meaning exists only at the boundaries, where physical variation meets interpretation, where a pattern in space becomes a decision in a circuit, where electrons moving in response to invisible oscillations are counted, compared, and turned into symbols we can use. At no point does the universe recognize that a message has been sent. It only evolves according to its rules. Understanding Wi-Fi, then, is not about learning a trick of modern technology. It is about seeing how deeply our inventions are woven into the behavior of the physical world. How much we rely on the quiet regularity of fields and waves. How much meaning we extract from motion that was never designed to carry it. And once that becomes clear, another question begins to take shape. If all wireless communication depends so completely on the structure of space and time, then the limits we experience, the dropouts, the delays, the congestion, are not failures of design alone. They are expressions of deeper constraints. Constraints that apply not just to Wi-Fi, but to every signal that has ever crossed the universe. Those limits are subtle, but they are everywhere. And they are what we need to understand next. Those limits begin with something deceptively simple: energy. Every Wi-Fi signal costs energy to produce. Electrons must be pushed back and forth. Fields must be disturbed. That energy spreads outward as the wave propagates, distributing itself across an ever-growing region of space. The farther the wave travels, the more thinly that energy is spread. Nothing is being lost in a mysterious way. It is simply being shared with a larger and larger volume. This is why signal strength falls with distance. Not because the wave tires or fades, but because geometry demands it. A signal leaving an antenna spreads roughly like the surface of an expanding sphere. Double the distance, and the same energy is now distributed over 4 times the area. The field at any one point becomes weaker, even though the total energy carried by the wave remains conserved. Inside a room, this spreading happens quickly. Reflections complicate the picture, but the basic constraint remains. There is only so much energy available to shape the electromagnetic field in a way that can be reliably detected. Push too far, and the variations that once carried information sink into the background of thermal motion and environmental noise. This is where the idea of a threshold becomes unavoidable. Receivers do not need a strong signal. They need a signal that stands out. As long as the intended variations are distinguishable from randomness, communication is possible. Once they are, not interpretation fails abruptly. This is why Wi-Fi often feels binary to us. Either it works or it doesn't. The underlying physics degrades smoothly, but our ability to extract meaning collapses suddenly when uncertainty crosses a critical point. Power alone cannot solve this. Increasing transmission power does strengthen the signal, but it also raises interference for everyone else sharing the same space. Because electromagnetic waves pass through one another, every transmitter contributes to the background environment. Too much power does not clarify communication, it saturates it. This is why Wi-Fi operates under strict power limits and relies instead on structure, timing, and cooperation between devices. The air is not owned by any one transmitter. Every Wi-Fi device must negotiate access to the shared electromagnetic environment. Before transmitting, a device listens. It senses whether other signals are present. If the space is busy, it waits. If it detects a gap, it transmits briefly, then releases the channel again. This back and forth happens constantly, faster than we can perceive, creating the impression of a continuous connection even though the channel is shared in time. Congestion, then, is not about too many signals colliding. It is about too many devices trying to speak politely at once. Each device follows the same basic rules. Each tries to minimize disruption. But as the number of participants grows, the available quiet moments shrink. Waiting times increase. Effective speed drops. Not because the physics has changed, but because coordination has become harder. This coordination depends on trust. Wi-Fi protocols assume that devices will follow agreed-upon behaviors. They assume that transmitters will not dominate the channel unfairly. They assume that errors will be reported honestly and retransmissions requested when needed. These assumptions are not enforced by physics. They are enforced by design. And when they are violated, intentionally or accidentally, performance suffers for everyone. Even here, though, the deeper constraint is still physical. Every coordination scheme relies on timing signals that must themselves be transmitted and received. Those signals are subject to the same delays, reflections, and noise as everything else. There is no layer that escapes the field. There is no abstract control plane floating above reality. Everything ultimately reduces to patterns of electromagnetic variation, interpreted under uncertainty. This is why latency exists. Inside a home network, delays are small, but they are never zero. Signals take time to propagate. Devices take time to respond. Decisions take time to be made and acted upon. Each step is bounded by how fast physical changes can occur and be detected. These delays accumulate, not in dramatic ways, but in subtle ones that shape how systems feel to us. When Wi-Fi feels responsive, it is because these delays are short compared to human perception. When it feels sluggish, it is because they begin to align in unfortunate ways. A busy channel here, a retransmission there, a moment of poor signal quality that forces the system to slow down and re-establish reliability. None of this is a bug. It is the cost of building meaning on top of motion. What makes this remarkable is how stable the whole arrangement is. Despite constant movement, interference, and uncertainty, Wi-Fi connections usually persist. They adapt. They recover. They maintain coherence over time. This stability does not come from rigidity. It comes from feedback. Every receiver reports back what it sees. Every transmitter adjusts based on that feedback. Data rates rise when conditions are good and fall when they are not. Modulation schemes shift. Error correction strengthens or relaxes. The system is always probing the boundary between clarity and confusion, trying to operate as close to it as possible without crossing over. This boundary is not fixed. It moves as people walk through rooms, as doors open and close, as devices turn on and off, as the electromagnetic environment reshapes itself moment by moment. Wi-Fi works because it never assumes the world is still. It assumes the opposite and builds flexibility into its core. Seen this way, Wi-Fi is less like a pipeline and more like a conversation held in a crowded space. Voices overlap. Pauses matter. Misheard words are corrected. Meaning emerges not from perfect transmission, but from shared expectations and continuous adjustment. And that brings us to a deeper realization. The same principles that govern Wi-Fi govern every form of communication we know. From radio broadcasts crossing continents to light leaving distant stars, the story is the same. Energy spreads. Fields evolve. Meaning is inferred under uncertainty. There is no shortcut, no hidden channel, no escape from the structure of space and time. Wi-Fi does not bend the rules of the universe to make information convenient. It reveals what those rules have always allowed. And once you see that, the technology fades into the background. What remains is a picture of a universe that is quietly capable of carrying structure across emptiness. Not because it intends to, but because its laws make it possible. That quiet capability is what everything else is built on. And understanding it changes how ordinary things feel. Because the next time a signal connects, you are not witnessing something abstract or artificial. You are watching space itself, moment by moment, doing exactly what it knows how to do. Once you notice that, it becomes difficult to think of Wi-Fi as a separate layer sitting on top of reality. It is not an overlay. It is a direct expression of how the electromagnetic field behaves when we learn how to shape it carefully. What we often call wireless technology is really an agreement with nature. We accept the limits imposed by fields, by energy, by noise, by time, and then we ask a very specific question. Given those limits, what patterns can reliably survive? Everything that follows is an answer to that question. One of the most important of those answers is redundancy. At first glance, redundancy feels inefficient. Why repeat information? Why spread it across multiple frequencies or transmit it more than once? But redundancy is not waste. It is an acknowledgement of uncertainty. It is a way of making meaning resilient when the medium itself is unpredictable. When a Wi-Fi signal is transmitted, the information it carries is rarely placed in a single fragile form. Instead, it is distributed across many small pieces, each one carrying part of the structure. Some pieces will arrive clearly. Others will be distorted. A few may disappear entirely. The receiver does not panic when this happens. It expects it. Because the receiver is not looking for perfection. It is looking for consistency. This is why error correction exists, not as a patch for bad physics, but as a natural response to it. Error correction works by embedding additional structure into the signal. Patterns that allow the receiver to notice when something has gone wrong, and often to infer what the original signal must have been. Again, nothing about this is symbolic at first. The receiver does not see an error. It measures voltages. It compares timings. It notices when relationships between parts of the signal no longer line up as expected. From that mismatch, it concludes that interference or noise has altered the wave. The universe never announces mistakes. It only evolves. Correction is something we impose afterward, by carefully designing how variation is interpreted. There is a quiet elegance here. Wi-Fi does not try to eliminate noise. It treats noise as part of the environment and designs around it. It accepts that some uncertainty is unavoidable and then asks how much uncertainty can be tolerated before meaning collapses. This tolerance is not fixed. It depends on context. When conditions are good, when the signal is strong and interference is low, Wi-Fi systems take advantage of that clarity. They encode more information into each oscillation. They use finer distinctions in phase and amplitude. The result is higher data rates, achieved not by transmitting faster through space, but by packing more structure into the same physical motion. When conditions worsen, the system retreats. It simplifies the encoding. It spreads information more broadly. Data rates drop, but reliability increases. The connection remains usable because the interpretation becomes more conservative. This adaptability is often mistaken for intelligence. In reality, it is feedback. The receiver continuously reports what it is able to distinguish. The transmitter continuously adjusts how boldly it shapes the wave. Neither side understands the content of the information in any human sense. They are responding to physical constraints moment by moment, using rules that were designed with those constraints in mind. What makes this feel almost alive is that the adjustment never stops. Even when you are sitting still, the environment is not. Air moves, materials vibrate. Other devices transmit briefly and fall silent again. The electromagnetic field in a room is never static. Wi-Fi succeeds because it does not expect stability. It expects fluctuation and treats it as normal. This is also why Wi-Fi behaves differently in different places. A large open room with smooth walls produces different reflection patterns than a cluttered space full of furniture and people. A crowded apartment building creates a denser background of overlapping transmissions than a quiet house in a rural area. None of these differences are abstract. They are geometric and material. They shape how waves propagate, interfere, and decay. Your device does not know where it is in any conceptual sense. It only knows what the electromagnetic field around it is doing. Its behavior changes because the field changes, not because the environment has been labeled. This brings us to an important distinction that is easy to miss. Wi-Fi does not create a connection in the way a wire does. A wire constrains the path along which charges can move. It enforces geometry. Wi-Fi does not enforce a path. It creates a shared field of possibilities. Communication happens wherever the transmitter and receiver can maintain a consistent interpretation of that field. This is why wireless connections feel spatially diffuse. You can move a device a little and still remain connected. You can turn it slightly and watch the signal strength change. You can place your hand near an antenna and alter the reception. All of this happens because there is no single route the signal must follow. There are many overlapping paths, many ways for energy to arrive, many ways for meaning to be reconstructed. And yet, despite this flexibility, there are hard limits. One of those limits is bandwidth. Bandwidth is often described as a property of channels or frequencies, but physically, it is a measure of how much variation a system can support over time. A narrow bandwidth means only slow, gentle changes can be distinguished. A wide bandwidth allows faster, more complex variations to be resolved. In electromagnetic terms, bandwidth corresponds to how wide a slice of the frequency spectrum a system uses. The wider the slice, the more independent oscillations are available to carry structure. The more structure you can impose, the more information you can encode. But bandwidth is not infinite. The electromagnetic spectrum is shared. Different systems occupy different regions to avoid interfering with one another too severely. Regulations exist not because nature demands them, but because coordination does. Without agreed-upon boundaries, communication would quickly degrade into incoherent noise. Even within those boundaries, practical limits arise. Circuits can only respond so quickly. Antennas only couple efficiently over certain ranges. Materials absorb and distort some frequencies more than others. Every increase in bandwidth brings new challenges in design and stability. This is why Wi-Fi standards evolve. Each new generation does not change the underlying physics. It explores the edges of what is already possible. It uses more sophisticated ways of shaping waves, more careful timing, more detailed feedback. Progress comes not from violating limits, but from approaching them more closely without crossing them. There is a quiet humility in this. No part of Wi-Fi assumes the universe will cooperate beyond what it already does. There is no demand for special behavior. The system works because it respects the rules it depends on. When people speak about wireless communication as if it were magical, what they are often responding to is not mystery, but unfamiliarity. The physics is subtle, but it is consistent. Once you see the consistency, the wonder does not disappear. It deepens. Because Wi-Fi is not impressive, because it is fast or invisible. It is impressive because it works at all. It works because the electromagnetic field is stable enough to support waves, because those waves propagate predictably, because matter responds to fields in repeatable ways, because energy spreads but does not vanish, because noise is random enough to be distinguished from structure. These are not technological achievements. They are properties of the universe. Technology enters only in how carefully we learn to align ourselves with them. And this alignment extends far beyond our homes and devices. The same principles that allow a router to speak to a laptop allow radio telescopes to listen to distant galaxies. They allow spacecraft to remain in contact across billions of kilometers. They allow light from the early universe to reach us, carrying faint imprints of conditions that no longer exist. In every case, meaning travels not because it is carried intentionally, but because the physical medium allows the patterns to persist. Seen from this perspective, Wi-Fi becomes a small, everyday example of a much larger truth. The universe is not silent. It is full of motion, structure, and constraint. We do not insert information into it so much as discover which patterns it can support, and then learn how to read them. And when we do, the boundary between the ordinary and the cosmic quietly dissolves. Because the same space that carries a video stream across your living room is the space that carries starlight across billions of years. It does so patiently, impartially, according to rules that never mention purpose or meaning. Meaning is something we add at the end, and that may be the most remarkable part of all. Once that perspective settles in, it becomes clear that Wi-Fi is not a special case. It is simply one place where we've learned to cooperate with the structure of the electromagnetic field in a very deliberate way. What makes it feel different from older technologies is not the physics, but the density of coordination involved. In early radio communication, a single transmitter spoke to many receivers. The signal was strong, the encoding was simple, and the environment was comparatively quiet. Interpretation was coarse, but forgiving. With Wi-Fi, the situation is reversed. Many devices speak briefly to one another, sharing the same space, each shaping the field only slightly, each relying on precise timing and mutual awareness to avoid confusion. This density forces a different kind of discipline. A Wi-Fi device cannot assume that the electromagnetic environment will remain stable even for a fraction of a second. It cannot assume that silence means absence. It cannot assume that what it senses now will still be true a moment later. Every decision must be provisional, ready to be revised as soon as new physical evidence arrives. This is why Wi-Fi is built around listening as much as speaking. Before transmitting, a device measures the field. It listens for patterns that indicate activity. It estimates how crowded the space is, not conceptually, but physically, by detecting energy at particular frequencies and times. From that measurement, it decides whether to wait or to act. Waiting is not passive. While waiting, the device continues to observe. It refines its expectations. It adjusts its internal timing. It prepares to respond quickly when an opportunity appears. Communication, in this sense, is less like sending a message and more like entering a rhythm. When a device does transmit, it does so briefly. It shapes the field, releases it, and then falls silent again. This brevity is intentional. Long transmissions would monopolize the space, increasing the chance of interference and reducing overall reliability. Short transmissions allow many participants to coexist, each contributing small, well-defined patterns to the shared field. From above, this looks chaotic. From within the system, it is orderly. Order emerges because all participants are responding to the same physical constraints. No device can ignore the field. No device can transmit without being heard by others nearby. Cooperation is not enforced by authority. It is enforced by physics. This is why Wi-Fi performance degrades gracefully rather than catastrophically. As conditions worsen, devices adapt. They wait longer. They transmit more conservatively. They accept lower speeds in exchange for continued coherence. Communication slows, but it rarely collapses entirely unless the physical limits are truly exceeded. And when it does collapse, the reason is always physical. A signal becomes too weak to distinguish from noise. Timing becomes too uncertain to maintain synchronization. Interference becomes too dense to resolve structure. At no point does the system decide to fail. It simply reaches a state where interpretation is no longer reliable. Understanding this removes a subtle but persistent illusion. We often imagine that information exists independently, waiting to be transmitted. That communication is about moving something from one place to another. But in reality, information only exists where interpretation succeeds. It is not transported like an object. It is reconstructed again and again from physical evidence. Every Wi-Fi receiver is not receiving information. It is continuously inferring it. That inference is grounded in probability. The receiver asks not what was sent, but what is most consistent with what I am observing, given what I expect. As conditions change, the confidence of that inference changes as well. When confidence drops too low, the system pauses, requests clarification, or tries again. This probabilistic nature is not a weakness. It is the only way communication can exist in a universe governed by continuous fields and unavoidable noise. Once you see that, the distinction between analog and digital begins to blur in a meaningful way. Digital systems do not eliminate uncertainty. They manage it. They define boundaries within which uncertainty can be tolerated and beyond which meaning is withdrawn. Wi-Fi sits precisely at that boundary. It operates as close as possible to the edge of interpretability, where small changes in physical conditions can have noticeable effects. This is why moving a device slightly can change reception, why opening a door can alter signal quality, why the presence of people matters. The field is sensitive because it is being used efficiently. Efficiency here does not mean minimal energy or maximal speed. It means extracting as much structure as possible from a given physical situation without losing coherence. Wi-Fi systems are constantly probing how much variation the environment can support at any moment and adjusting themselves accordingly. This probing is invisible, but relentless. Every acknowledgement packet, every timing adjustment, every shift in modulation is part of an ongoing experiment. The system asks, "Can I be bolder?" and listens carefully to the answer. When the answer is yes, it moves closer to the limit. When the answer is no, it retreats. This behavior can feel almost intentional, but it is not. It is the emergent result of feedback loops grounded in physics. No device has a global picture. No device knows why conditions change. They only know what the field around them allows. And this brings us to a deeper appreciation of space itself. We often treat space as empty, passive, a backdrop against which events occur. Wi-Fi reveals that space is anything but passive. It has properties. It supports waves. It enforces speeds. It shapes how energy spreads and how patterns persist. Space is not a container. It is an active participant. The electromagnetic field fills space, but it is not something added on top of it. It is part of the structure of space as we understand it. Its behavior is woven into the geometry of the universe. When we transmit a Wi-Fi signal, we are not injecting something foreign. We are nudging an existing field into a particular pattern and letting it evolve. This evolution is constrained but generous. It allows waves to propagate without dispersing immediately. It allows interference to be predictable rather than chaotic. It allows different frequencies to coexist without annihilating one another. These are not trivial facts. They are deep features of the universe that could easily have been otherwise. If electromagnetic waves behaved slightly differently, if they scattered more strongly, if they interacted nonlinearly at everyday energies, if they decayed spontaneously, wireless communication as we know it would be impossible. Not difficult. Impossible. That it is possible at all tells us something profound about the kind of universe we inhabit. A universe where local changes can influence distant regions in a stable, repeatable way. A universe where fields carry structure without intention. A universe where matter responds reliably to invisible motion. Wi-Fi is not an anomaly in such a universe. It is an expression of it, and this realization quietly reframes the everyday. When you connect to a network, you are not accessing an abstract service. You are participating in a physical process that depends on the same principles that govern stars, plasmas, and the early cosmos. The scale is smaller, the energy is lower, but the rules are the same. Understanding that does not make Wi-Fi less impressive. It makes it more honest. Because the real achievement is not that we invented something new, but that we learned how to listen closely enough to what the universe already allows, and then build within those allowances, carefully, patiently, without demanding exceptions. That quiet cooperation is what makes the connection possible. And it is the same cooperation that underlies every signal that has ever crossed space, carrying structure from one place to another, waiting to be noticed, waiting to be interpreted, waiting to become meaningful. That waiting is not passive. It is an invitation built into the structure of the field itself. Every electromagnetic wave that propagates through space carries with it the possibility of interaction. Not the certainty of being received, but the possibility of being felt. Whether that possibility becomes real depends on whether there is matter arranged in a way that can respond coherently to the wave's motion. This is why communication is always relational. A Wi-Fi signal does not exist for a device. It exists in space. The device exists in space as well. Communication happens only when their structures happen to line up in time, in frequency, and in geometry. The field does not choose sides. It simply evolves. This relational nature explains something that often feels counterintuitive. The same signal can be present everywhere, yet only some devices can use it. A router's transmission fills a room, but a device that lacks the right antenna, the right tuning, or the right interpretation rules will experience nothing at all. The wave is still there. The information is not. Information, in this sense, is not a substance. It is a compatibility. This compatibility is fragile, but it is also remarkably robust when maintained carefully. Wi-Fi systems are designed to preserve it under constant stress, not by enforcing control, but by continually re-establishing alignment. Frequencies are tracked. Timing is corrected. Phase relationships are monitored. The system never assumes that yesterday's conditions still hold today. This is one reason why connection is a process rather than an event. When a device connects it to a Wi-Fi network, it does not simply join. It negotiates. It listens. It exchanges brief signals that establish shared expectations about timing, frequency, and encoding. Only after that alignment is achieved does meaningful data flow begin. Even then, the alignment is provisional. The moment conditions change, a new device appears, a wall shifts, interference increases, the assumptions underlying the connection are adjusted. Data rates change. Error, tolerance shifts. The connection breathes with the environment. This breathing is not a metaphor. It is literal. The field around you is constantly changing, and your devices are constantly adapting to those changes. The motion of electrons in an antenna, the oscillation of fields in space, the timing of signals in circuits, all of it forms a coupled system that is never at rest. And yet, from the outside, it feels stable. This apparent stability is one of the most striking features of modern communication systems. We have built layers of interpretation on top of physical motion that allow meaning to persist even when the underlying signals are noisy, incomplete, or distorted. We experience a steady connection because the system is continuously compensating for instability beneath the surface. This compensation has limits. There are environments where Wi-Fi struggles not because the technology is flawed, but because the physical constraints become too severe. Thick metal walls reflect and absorb waves. Dense crowds of devices saturate available channels. Strong interference overwhelms subtle variations. In these cases, no amount of clever encoding can restore clarity. The failure is not moral or technical, it is physical. Recognizing this changes how we think about improvement. Progress in Wi-Fi does not come from demanding that space behave differently. It comes from understanding space more deeply, from learning which patterns survive which conditions, from refining how we probe the field and how we interpret its response. This is why advances often feel incremental rather than revolutionary. Each new standard builds on what came before, squeezing a little more structure out of the same physical medium. The leaps are not in physics, but in insight, in realizing that a certain pattern can be distinguished after all, that a certain timing scheme can be stabilized, that a certain kind of interference can be mitigated rather than avoided. These insights accumulate slowly. They also generalize. The techniques developed for Wi-Fi do not stay confined to homes and offices. They inform cellular networks, satellite communication, radar systems, and even experimental physics. The same ideas about modulation, error correction, and adaptive feedback appear wherever signals must survive uncertainty. This cross-pollination is not accidental. It reflects the fact that all of these systems are negotiating with the same field, subject to the same constraints. Lessons learned in one context often apply elsewhere, once the scale and conditions are adjusted. At the deepest level, this is what it means to do physics-based engineering. You do not impose behavior. You discover what is possible and then work within those possibilities. You respect the medium not because it is fragile, but because it is consistent. The rules do not bend, but they can be approached from many angles. Wi-Fi is a quiet example of this philosophy in action. It shows how much can be achieved without ever violating a fundamental law, how much structure can be layered onto continuous motion, how much meaning can be reconstructed from subtle variation. It also reminds us of something easy to forget. Every connection we rely on is contingent. It depends on fields continuing to propagate as expected, on matter continuing to respond predictably, on noise remaining random enough to be distinguished from signal, on timing remaining stable enough to synchronize interpretation. These conditions usually hold. They hold so reliably that we stop noticing them. But they are not guaranteed by intention. They are guaranteed only by the nature of the universe as it happens to be. This realization does not make communication feel precarious. It makes it feel grounded. Because the same stability that allows Wi-Fi to work allows atoms to hold together, allows light to travel across space, allows physical laws to be discovered and reused. The electromagnetic field does not selectively cooperate. It behaves the same way everywhere, for everything. We benefit from that impartiality. In a different universe, one with slightly different field equations, slightly different interactions, wireless communication might be impossible, or trivial, or unnecessary. The fact that it exists here, in this particular form, is a reflection of the specific balance of constraints that define our world. Wi-Fi, then, is not just a convenience. It is a small window into the deep regularities of nature. A reminder that space is not empty, that motion can carry structure, that meaning can emerge from patterns that were never designed to have meaning at all. Every time a signal connects, that quiet truth is being enacted again, invisibly, patiently, according to rules that have been in place long before we learned how to use them. And those rules are still at work, shaping every interaction, whether we notice them or not. Noticing that patience changes how the entire system feels. It becomes clear that Wi-Fi is not fast because it rushes, but because it aligns. It aligns with rhythms that are already there, with oscillations that space naturally supports, with responses that matter reliably produces when fields change around it. Speed, in this sense, is a byproduct of harmony rather than force. This is why attempts to simply push harder so often fail. There is a temptation to imagine that stronger signals, higher power, or more aggressive transmission would solve the problems we experience. but beyond a certain point, pushing harder only increases disorder. The field becomes crowded. Interference grows. Receivers struggle to distinguish intention from coincidence. Clarity is not achieved by amplification alone. Clarity comes from precision. Precision in frequency selection, precision in timing, precision in how variation is introduced and how it is measured. Each of these requires restraint as much as effort. A Wi-Fi transmitter must know not only how to speak, but when to remain silent. Silence is not wasted time. It is part of the structure that allows meaning to persist. Without silence, there would be no reference against which variation could be detected. In this way, absence becomes as important as presence. The electromagnetic field is always active. It is never truly quiet. But relative quiet, moments when intentional structure is not being imposed, creates contrast. That contrast is what allows receivers to lock on, to synchronize, to prepare themselves to interpret what comes next. This interplay between activity and restraint is not unique to Wi-Fi. It appears everywhere waves are used to carry information. Music relies on silence as much as sound. Vision relies on contrast as much as illumination. Communication relies on structure as much as energy. Seeing Wi-Fi through this lens reveals why it feels so sensitive to context. A crowded environment is not just loud. It is saturated with overlapping intentions. Each transmitter imposes its own structure on the field, briefly, repeatedly. The receiver must disentangle these structures, deciding which belong together and which do not. As the number of participants grows, the problem becomes less about signal strength and more about discrimination. Discrimination, here, is not exclusion. It is pattern recognition. The receiver looks for consistency, for relationships that persist across time and frequency in ways that random fluctuations rarely do. It asks which variations belong to the same source, which arrive with the right timing, which align with expected structure. This is a statistical process grounded in physics, not a symbolic one. And it works because the field behaves linearly. At the energies used by Wi-Fi, electromagnetic waves do not distort one another. They pass through, overlap, and add without, permanently altering each other's structure. This linearity is crucial. Without it, disentangling signals would be far more difficult, perhaps impossible. Overlapping transmissions would merge irreversibly, destroying the information they carried. That they do not is a gift of the equations governing the field. Linearity allows superposition. Superposition allows separation. Separation allows interpretation. Again, nothing about this is guaranteed in principle. It is a property of the particular universe we inhabit. This linearity also explains why interference behaves the way it does. Interference is not a collision. It is the result of overlapping patterns adding together. At some points in space and time, they reinforce. At others, they cancel. The resulting pattern is complex but predictable. And because it is predictable, systems can be designed to cope with it. Coping does not mean eliminating interference. It means understanding its structure well enough that it can be treated as another constraint rather than an obstacle. This understanding leads to an important reframing. Wi-Fi does not compete with interference. It incorporates it. Reflections, multipath effects, and overlapping transmissions are not always enemies. Under the right conditions, they can provide additional information. Multiple delayed copies of a signal can improve reliability. Slight variations in phase across antennas can reveal spatial structure. What once seemed like distortion becomes a resource when interpreted correctly. This shift in perspective is subtle, but powerful. Instead of trying to force the environment into simplicity, modern communication systems accept complexity and learn to navigate it. They do not demand a clean channel. They construct meaning in messy ones. This is why progress in Wi-Fi feels invisible most of the time. New standards rarely feel revolutionary to the user. Connections become slightly more stable. Speeds become slightly more consistent. Dropouts become slightly less frequent. The improvements are incremental because they operate close to physical limits. But those increments matter. Each refinement represents a deeper understanding of how the electromagnetic field behaves in real environments. Each one reflects countless experiments, measurements, and adjustments, all grounded in the same fundamental physics. What we call technology here is really accumulated insight. Insight into how electrons move when fields change. Insight into how waves propagate through cluttered spaces. Insight into how noise behaves statistically. Insight into how interpretation can remain reliable under uncertainty. Wi-Fi is not a triumph over nature. It is a collaboration with it. That collaboration also has an ethical dimension, even if it is rarely discussed. Because the electromagnetic spectrum is shared, decisions about how it is used affect everyone. Power limits, frequency allocations, and protocol designs shape who can communicate, how, reliably, and under what conditions. These decisions are not purely technical. They are choices about coordination in a shared physical space. The field does not enforce fairness. It enforces consistency. Fairness must be designed. This is why standards exist, why regulations exist, why devices are expected to behave in certain ways. Without these agreements, the shared environment would quickly degrade into incoherence. Not because anyone intended harm, but because uncoordinated behavior scales poorly. Wi-Fi works as well as it does because most participants follow the same rules. Not rules imposed by authority, but rules discovered through experience. Rules that reflect what the field will tolerate. Breaking those rules does not produce freedom. It produces noise. This realization brings us back to the deeper theme that has been quietly unfolding. Communication is not about domination. It is about alignment. Alignment with the medium. Alignment with other participants. Alignment with the constraints that make meaning possible. Wi-Fi is a reminder of this, playing out thousands of times per second in every connected space. It shows that reliable interaction does not come from overpowering the environment, but from listening closely to what it allows. And that lesson extends far beyond wireless networks. It applies wherever patterns must persist across distance and time, wherever meaning must survive uncertainty, wherever cooperation emerges not from command, but from shared structure. In that sense, Wi-Fi is not just a tool we use. It is a quiet demonstration of how understanding turns limitation into possibility. And once that understanding is in place, the field that once felt empty begins to feel full, not of messages, but of potential. Potential that is always there, waiting. That potential does not announce itself. It does not signal readiness or intention. It simply exists, woven into the behavior of fields and matter, waiting for structures capable of responding to it coherently. This is why the most important part of any communication system is not the signal itself, but the receiver. A Wi-Fi receiver is not impressive because it hears the faint waves. It is impressive because it knows how to listen. It knows what to ignore, what to amplify, what to compare, and what to discard. It knows which patterns matter and which are likely coincidences. That knowledge is not conscious, but it is deeply embedded in the design of the system. Listening, in this sense, is an active physical process. The receiver does not passively record whatever reaches it. It shapes the incoming signal through filters, amplifiers, and timing circuits. It aligns its internal rhythms with the external field. It continuously adjusts its expectations based on what it observes. Each adjustment changes how future signals are interpreted. This feedback loop is essential. Without it, even a strong signal would drift out of alignment. Small timing errors would accumulate. Phase relationships would blur. Meaning would dissolve. Stability is not achieved once and maintained. It is achieved repeatedly, moment by moment, through continuous correction. This need for correction reveals something important about time. In everyday language, we treat time as a uniform flow that everything shares automatically. In communication systems, time must be constructed. Devices must agree not only on what patterns mean, but on when they occur. That agreement cannot be assumed. It must be established physically. Synchronization is the name we give to this process. A Wi-Fi receiver locks onto the timing of an incoming signal by detecting regular features in the wave, repeating structures that act as anchors in time. These anchors allow the receiver to align its internal clock with the transmitter's rhythm. Once aligned, interpretation becomes possible. When alignment drifts, interpretation degrades. This drift is inevitable. No two clocks remain perfectly synchronized forever. Thermal noise, component imperfections, and environmental changes introduce tiny differences that grow over time. Wi-Fi systems compensate by continually resynchronizing, embedding timing references into the signal itself so that alignment can be refreshed. Again, nothing about this is abstract. Clocks are physical devices. Their stability is limited by material properties and energy constraints. Synchronization is not a logical operation. It is a physical negotiation carried out through fields and motion. Distance enters this negotiation in a subtle way. Although the speed of electromagnetic propagation is extremely fast on human scales, it is not infinite. Signals take time to travel. In small environments, this delay is negligible. In larger systems, it becomes significant. Synchronization must account for it. Timing references must be interpreted in light of expected delays. Feedback must be delayed and adjusted. Wi-Fi operates in a regime where these effects are small but not non-existent. The system is designed to tolerate them without requiring explicit correction. But the same principles apply, scaled up, in every long-distance communication system we have ever built. At larger scales, delay becomes unavoidable. Coordination becomes harder. Interpretation becomes more tentative. The physical limits of time and space assert themselves more strongly. This reminds us that Wi-Fi sits in a privileged middle ground. It operates at distances short enough that propagation delays are small, but large enough that spatial complexity matters. It lives in an environment where reflections, interference, and motion dominate over raw distance. This makes it an ideal laboratory for understanding how communication behaves in real, messy spaces. And what it shows us is that communication is never just about sending. It is about maintaining a shared frame of reference. That frame includes frequency, timing, phase, and expectation. It includes assumptions, about noise and interference. It includes trust that the other side will behave predictably. When any part of that frame erodes, communication falters. Rebuilding the frame takes time and energy. This is why reconnecting to a network is not instantaneous. Devices must reestablish alignment. They must rediscover which frequencies are usable, which timing references are stable, which patterns can be relied upon. This process is often hidden from the user, but it is always there. Seen this way, a connection is not a static state. It is a dynamic equilibrium, an ongoing balance between signal and noise, structure and uncertainty, intention and interpretation. The balance shifts constantly, but as long as it remains within tolerable bounds, meaning persists. This persistence is fragile but not delicate. Fragile systems shatter under stress. Wi-Fi bends. It adapts. It slows down. It simplifies. It does whatever is necessary to remain interpretable. Only when the environment becomes truly hostile does it fail. This resilience is not accidental. It is the result of designing systems that accept the world as it is, rather than demanding that it be simpler. And that acceptance points toward a broader lesson. Many of the systems we rely on every day, communication networks, power grids, even social structures, face similar challenges. They operate in environments that are noisy, unpredictable, and shared. They must coordinate without central control. They must adapt continuously to changing conditions. The strategies that allow Wi-Fi to function under these constraints are not unique. They reflect general principles about how structure can persist in complex environments. Redundancy, feedback, adaptation, respect for limits. These are not technological tricks. They are patterns that appear wherever stability must be maintained without rigidity. Wi-Fi, in its quiet way, demonstrates this beautifully. It shows that order does not require isolation, that meaning does not require certainty, that cooperation can emerge from shared constraints rather than imposed control, and it shows that understanding the medium is more powerful than trying to overpower it. When you next connect to a network, nothing visible changes. There is no flash, no motion, no sign that anything has happened at all. But beneath that stillness, space has been gently shaped into a pattern. Matter has responded. Fields have evolved. Interpretation has begun. The universe has done what it always does. It has allowed structure to persist briefly in motion, and that is enough. Once you begin to see communication this way, the distinction between signal and environment becomes less sharp. A Wi-Fi transmission is not something laid on top of space. It is something that uses space. The electromagnetic field is already present everywhere, already capable of supporting oscillation, already governed by stable relationships between electric and magnetic change. A transmitter does not create a new medium. It briefly reshapes an existing one and then releases it again. That reshaping is subtle. The variations imposed on the field are small compared to the field's overall capacity for motion. They must be small because large disturbances would be inefficient, disruptive, and difficult to coordinate with others. Wi-Fi works in a regime where signals are gentle enough to coexist, yet structured enough to be distinguished. This balance is delicate, but it is also remarkably forgiving, because the underlying field behaves so predictably. Predictability is what allows interpretation to exist at all. When a receiver measures an incoming signal, it is never measuring the signal alone. It is measuring the sum of everything happening in that frequency range at that moment. The reason interpretation succeeds is that intentional structure tends to persist across time in ways that random fluctuations do not. A signal that has been deliberately shaped will exhibit correlations, relationships between moments, frequencies, and phases that noise rarely mimics for long. The receiver looks for those relationships, not for isolated values. This is why Wi-Fi systems rely so heavily on comparison rather than detection. They compare what is happening now to what happened a moment ago. They compare one frequency band to another. They compare the phase of a wave at one antenna to the phase at another. Meaning emerges from consistency across these comparisons. When consistency holds, confidence grows. When it weakens, confidence drops and the system adjusts. Adjustment is constant because the environment is never still. Even in an empty room, the electromagnetic field is in motion. Thermal radiation fills space. Distant transmitters contribute faint signals. The walls themselves absorb and re-emit energy in subtle ways. Wi-Fi does not attempt to freeze this motion. It treats it as the baseline condition. Communication is built on top of motion, not in spite of it. This is also why location matters in ways that feel almost uncanny. A device moved a few centimeters may experience a noticeably different signal, not because the transmitter has changed, but because the pattern of interference at that location is different. Peaks and nulls form where waves reinforce or cancel. These patterns are stable enough to persist briefly, but sensitive enough to shift with movement. Wi-Fi operates within this shifting landscape, constantly sampling and adapting. Adaptation depends on feedback, and feedback depends on time. A receiver must tell the transmitter what it is seeing, and the transmitter must respond. That response cannot be instantaneous. It is delayed by propagation, processing, and scheduling. During that delay, conditions may change again. The system therefore never converges on a perfect state. It hovers near one, always correcting, never settling. This hovering behavior is not a flaw. It is a strategy. By remaining flexible, the system avoids becoming brittle. When conditions improve, it takes advantage. When they worsen, it retreats gracefully. Performance fluctuates, but coherence is preserved as long as the underlying physical constraints allow it. These constraints ultimately trace back to the properties of the electromagnetic field itself. The field supports waves that propagate without dissipating immediately. It supports superposition without permanent distortion. It responds linearly to the energies involved in everyday communication. These properties are not guaranteed by logic or necessity. They are contingent facts about the universe we inhabit. Wi-Fi exists because those facts happen to be favorable. Seen in this light, wireless communication feels less like a triumph of cleverness and more like an act of careful listening. Engineers did not invent new behaviors for space. They learned which behaviors already existed and then designed systems that could ride them reliably. Every protocol, every modulation scheme, every synchronization method is an expression of that learning. This is why improvements tend to be subtle. There is no dramatic leap beyond the field's limits, only incremental refinement in how closely those limits can be approached without crossing them. Each refinement represents a deeper understanding of how structure survives in motion, how meaning can be reconstructed from partial evidence, how coordination can emerge in a shared medium. At this point, Wi-Fi stops feeling like a special technology and starts feeling like a case study, a demonstration of how order can arise without control, how cooperation can be enforced by shared constraints, how stability can emerge from continuous adjustment rather than rigidity. The lessons it offers are not confined to communication. They apply wherever systems must function in noisy, shared, unpredictable environments. What makes Wi-Fi feel so invisible is not that it is simple, but that it is well matched to the world it inhabits. Its signals are shaped to the scale of rooms and walls. Its timing is tuned to the pace of everyday motion. Its power is limited to avoid overwhelming its own medium. It fits, and because it fits, it disappears from attention, until it doesn't. When a connection falters, we glimpse the underlying negotiation again. The pauses, the retrees, the shifting data rates, the quiet struggle to maintain alignment. These moments are not failures of intention. They are moments when the physical world asserts itself more strongly, reminding us that communication is always conditional. Conditional, but still remarkable. Because despite all of this, despite noise, motion, interference, delay, we routinely manage to shape space in ways that allow meaning to persist across distance. We do this not by escaping physics, but by working patiently within it. We do it by accepting uncertainty and building systems that can live with it. That acceptance is the true foundation of Wi-Fi, and it is the same foundation beneath every signal that has ever crossed space. From the faintest radio whisper to the oldest light in the universe, carrying structure forward, waiting for something capable of noticing. Once you begin to think this way, the everyday language we use around wireless technology starts to feel slightly misleading. We speak as though devices send and receive information, as though something complete and intact travels from one place to another. But what actually happens is more tentative. A transmitter creates a pattern. That pattern spreads. A receiver samples the result and tries to infer what must have been intended. Communication is not the transport of certainty. It is the reconstruction of likelihood. This is why reliability is never absolute. It is always statistical. A receiver does not know that it has interpreted a signal correctly. It only knows that, given what it has observed and what it expects, one interpretation is far more probable than the others. As long as that probability remains high enough, the system proceeds as though meaning is secure. When it drops, the system slows down, asks for confirmation, or tries again. What makes this workable is that the universe is not adversarial. Noise is random, but it is not malicious. It does not conspire to mimic structure indefinitely. Random fluctuations can briefly resemble intentional patterns, but they rarely sustain the relationships required to pass repeated checks. Over time, structure stands out simply because it is consistent. Wi-Fi exploits this fact relentlessly. It does not rely on a single measurement or a single moment. It relies on accumulation, on repeated confirmation, on the quiet confidence that grows when many small pieces line up in the same way. This accumulation happens quickly, far faster than we notice, but it is never instantaneous. This also explains why error correction feels invisible when it works and frustrating when it doesn't. Most of the time, small distortions are corrected before they ever reach awareness. The system quietly fills in what was lost or distorted, guided by the structure it expects to see. Only when the distortions become too severe does the correction fail, and the gaps become visible to us as pauses, glitches, or disconnections. At that moment, it can feel as though the system has suddenly broken. In reality, it has been struggling for some time, operating closer and closer to the edge of interpretability. The failure is not sudden. Our awareness of it is. This edge is defined by physics, not by design. No amount of clever encoding can make a signal stand out when its energy is comparable to the random thermal motion of electrons in the receiver. No amount of protocol sophistication can recover information that has left no distinguishable trace in the field. There is a point beyond which interpretation is no longer meaningful, and Wi-Fi systems are built to recognize when that point has been reached. Recognizing limits is as important as pushing them. A system that refuses to acknowledge uncertainty becomes unstable. A system that adapts to uncertainty can remain useful even when conditions are poor. Wi-Fi belongs firmly in the second category. It trades peak performance for resilience, and in doing so, it becomes something we can rely on. Reliance here does not mean perfection. It means predictability. When conditions are good, performance improves. When they are bad, performance degrades in understandable ways. The behavior is not mysterious. It follows from how waves propagate, how energy spreads, and how interpretation works under noise. Understanding this changes how frustration feels. A dropped connection stops feeling like a betrayal and starts feeling like a boundary. The system has reached a point where the physical evidence is no longer sufficient to support confident interpretation. That boundary may shift with a small change in position, orientation, or environment, but it is real. This perspective also reveals why wireless communication scales the way it does. Adding more devices does not just divide available bandwidth. It increases uncertainty. Each new transmitter adds structure to the field, but it also adds potential confusion. The system must work harder to distinguish which variations belong together. Coordination overhead grows. Waiting times increase. These effects are not flaws. They are the cost of sharing a medium. Sharing is unavoidable because the medium itself is shared. The electromagnetic field does not belong to any one device. It exists everywhere, responding impartially to all disturbances. Any system that uses it must therefore coexist with others doing the same. Wi-Fi is designed with this coexistence in mind. Its rules are not arbitrary. They are compromises shaped by experience. Those compromises extend beyond technology into policy. Frequency allocations, power limits, and standards are social agreements layered on top of physical constraints. They exist because uncoordinated use would quickly undermine everyone's ability to communicate. The field enforces no fairness on its own. Fairness must be engineered. Even so, engineered fairness only works because the field itself is consistent. Agreements are meaningful only if the medium behaves the same way for everyone. The predictability of electromagnetic propagation makes shared rules possible. Without that predictability, coordination would collapse into chaos. All of this points back to a central, quiet insight. Wi-Fi works not because we have mastered space, but because space is regular enough to be worked with. The field does not adapt to us. We adapt to it. Our devices succeed to the extent that they respect the structure they depend on. This respect is rarely visible, but it is everywhere. It is in the careful choice of frequencies that balance penetration and capacity. It is in the power limits that prevent saturation. It is in the timing, schemes that allow many devices to take turns without explicit negotiation. It is in the error correction methods that assume imperfection rather than deny it. Seen together, these choices form a coherent philosophy. Communication is not about forcing clarity. It is about cultivating it under constraint. That philosophy scales upward. The same principles that govern Wi-Fi govern long-distance radio links, satellite communication, and deep space probes. As distances grow and delays increase, the margins tighten. Interpretation becomes harder. Feedback slows, but the underlying approach remains the same. Patterns are imposed. Responses are measured. Meaning is inferred probabilistically. At the largest scales, this process becomes almost poetic. Light leaves a distant galaxy carrying subtle imprints of the conditions under which it was emitted. That light travels for billions of years, spreading, redshifting, mingling with other radiation. When it finally reaches our instruments, it is faint and incomplete. And yet, by accumulating evidence and applying careful interpretation, we extract meaning from it. In that sense, Wi-Fi is a miniature version of a much older story. A story about how structure survives in motion, about how information is never truly transmitted, only inferred, about how understanding arises when we learn to listen to what the universe is already doing. The more clearly you see this, the less magical wireless communication feels, and the more profound it becomes. That listening, once learned, never really stops. It becomes a way of seeing the world rather than a technique applied to a single problem. When you understand Wi-Fi as inference rather than transport, the familiar metaphors fall away. There is no pipeline carrying information from one place to another. There is no packet traveling intact through space. There is only a field evolving, matter responding, and systems repeatedly asking whether the patterns they observe are still consistent enough to trust. Trust, here, is physical. It is earned through regularity, through the repeated confirmation that when a field is shaped in a certain way, matter responds in a predictable one. This predictability is not perfect, but it is stable enough to build upon. And so, layer by layer, we build systems that lean on that stability without ever assuming it will hold unconditionally. This is why Wi-Fi never truly locks in. Even in the most stable environment, the system continues to measure, adjust, and renegotiate. The connection you experience as steady is actually the result of constant micro-corrections, each one too small to notice, but together forming a continuous thread of coherence. That thread is fragile in the same way balance is fragile. It is not brittle, but it must be maintained. A slight shift does not break it, but a series of uncorrected shifts will. Wi-Fi remains usable because it never stops correcting. Correction, however, always comes at a cost. Each adjustment consumes time. Each confirmation consumes energy. Each retransmission occupies shared space. These costs are small individually, but they accumulate. This accumulation is what we experience as latency, congestion, and slowdown. They are not failures of intention. They are the visible price of maintaining coherence in a shared, noisy medium. Once you see this, the behavior of wireless networks stops feeling arbitrary. It becomes legible. Slowdowns at peak hours make sense. Improvements near a router make sense. Variations between rooms make sense. The system is not capricious. It is responding to physical conditions that change in space and time. This legibility is important because it shifts how we think about control. We often imagine that better technology means tighter control, more certainty, fewer fluctuations. Wi-Fi shows the opposite. Better performance comes from accepting fluctuation and designing systems that can live with it. Control is not imposed. It is distributed. Each device controls only itself. It listens. It adapts. It follows shared rules. No central authority dictates the exact behavior of the field. Order emerges because all participants are responding to the same constraints in compatible ways. This kind of order is quiet. It does not announce itself. It simply persists, and it is deeply physical. Nothing about Wi-Fi relies on abstract logic floating above reality. Every decision ultimately reduces to voltages crossing thresholds, oscillations aligning or drifting, energy rising above or sinking below noise. The digital world we experience sits on top of these continuous processes, but it never escapes them. This grounding is why wireless communication feels robust in a way that purely symbolic systems never could. Symbols alone can't survive noise. They require a physical substrate that behaves predictably enough to carry them. Wi-Fi works because the electromagnetic field provides such a substrate, not perfectly, but well enough. That well enough is doing a lot of work. It tells us that the universe does not need to be ideal to be usable. It does not need to eliminate randomness to allow structure. It only needs to constrain randomness in consistent ways. Within those constraints, meaning can be carved out. This is a powerful idea because it generalizes far beyond communication. Biological systems rely on it. Brains operate under noise, delay, and uncertainty, yet still produce stable perception and thought. Social systems rely on it. Coordination emerges not because everyone has perfect information, but because enough structure exists to align behavior. Even physical laws themselves can be seen this way, stable regularities emerging from underlying motion. Wi-Fi sits at an intersection of these ideas. It is engineered, but it is not arbitrary. It is digital, but it is not discrete at its foundation. It is modern, but it rests on principles that have been true for as long as fields have existed. Understanding it does not demystify the world. It remystifies it in a quieter way. If this calm exploration brought you a moment of clarity or quiet curiosity, a gentle like or a soft tap on subscribe truly helps keep this little corner of the universe glowing. And if you feel like it, tell me where in the world you're listening from tonight. Rest well, and until our next quiet journey.